So first of all, apologies for the technical trouble earlier this morning. Of course, it was schedule change. Didn't inconvenience you too much. So I'm going to talk about a project with a couple of summer interns, Chopin and Chan. And I should also say that we're relying critically on a number of libraries developed by Ivan Perez. So he's also quite instrumental in this, particularly for our right. So the Arpeggigon, what is that? Well, it's a software implementation of a hardware instrument called the Reactive that was stumbled across on YouTube a number of years back. And it looks like this. It's essentially a cellular automaton. You configure by placing tokens or counters on this surface. It's a grid of hexagons. And then you press play, and there's something called a play that bounces around among these tokens, and then you hit the token is found this way. And I will explain in a bit more detail what kind of sound, what kind of notes you play just a little bit. Okay. And the key point here is that this is an interactive cellular automaton, so you can actually perform this by on the fly configuring and reconfiguring, and it also has a number of performance controllers, sliders to that those synthesizers, for example. So some of the students can actually create quite nice performances on the fly. It's sort of a form of live coding, I suppose. I'm not very good though, as you will see, so I will sort of try not to do too much into a rush. We'll come back to that. Also, I should say, this is still a work in progress. Our research is quite limited, progressing slowly. So the current implementation has a number of shortcomings, and you might hear things like the timing isn't as robust as it should be, for example, because it's also been quite naive when it comes to that. But we can get back to those details later. Anyway, the whole thing is based on something called the harmonic table. It's a bit similar to what we saw this morning. So you have this hexagonal grid layout. And here we place the notes. This time is the usual 12 notes per octave. And the key point is that each direction here corresponds to a particular musical interval. Okay? So if you go north, it's a perfect fifth. If you go northeast, it's minor third. Northwest is minor third. Northeast is a major third. And if you go due east, it's a half step. So we need to sort of go from here to here to have a half step. And now, this was developed initially as an alternative to the normal piano-like keyboard. The key point here is that if you want to play, say, a major chord, you can just hit these three keys, for example. And you can transpose very easily by just moving your finger across, and you don't have to change your finger. So that's the background to this. But here we are going to use as a kind of cellular automaton. So you're using the cells, and you're going to place things in the cells and have things bounce around to make music or some description. So that's the idea. So the Arpeggigon then is a software realization of the Reactive, written in Haskell using FRT and reactive relations. So that's one of Ivan's libraries. And the motivation for this work was basically we want to sort of see if we can use these libraries to do something which we can claim is a full-fledged music application. So in a sense, we are more interested in the kind of issues that crop up when we try to program something like this, more that than that is actually being musically useful in any deep sense. That said, I think it's a very fun thing to play around with, and I think you get to explore a particular musical space if you do this. So I think actually it has artistic merit as well. But I guess opinions are divided, and you might have a strong opinion after you have sort of lived through my demo in a little bit. Anyway, I'll say a few more words before we go into the demo. So the program looks like this. These are the tokens that you can play on the grid. They all have different meanings. So starting with this is called start token. So you can place this wherever. And when we hit play, a playhead will be generated at that point and then sent out in the direction of the arrow. And you can turn these in 6 possible directions. When we hit something like this, that just means reflect the playhead in some different direction. Again, you can turn the arrow. Okay, and here they also make the corresponding sum, the node corresponding to the position we're at. This is a split. It will take an incoming playhead and split in 5 directions, all but the one from where the playhead came. Okay. This is a stop token. So we hit that, we play the note, and then the playhead vanishes. And this is absorption token. So if we hit that, no sound, this is metaphor. So these are the things we can play on the board, and again we can turn it in all possible directions. And then we have some simple controls over here as well. Things like tempo, the layer beat. So okay, we can also have a number of layers of this. So we can sort of have a number of machines running in parallel. I'll come back to that as well. Yes, and the volume and things like that. So I hope you get the basic idea. So now let me show you, I think, what this looks like. I said this was just a matter of exploring if you can use these libraries to do it then which we can argue is full-fledged in the sense of or how to deal with all problems to deal with to write something realistic. Okay. So let me get out of that mode. Let me get this up. Okay. So the signal level is a bit low from my synthesizer here, so it's perhaps a slightly noisy, but I hope you will hear reasonably well. So as you can see, I placed 2 start tokens on the grid here already. So now when I hit play, you should sort of see 2 playheads being generated, and you should hear sort of this node split taken like so. And you see how these nodes go away.
Well, you don't sound if you don't hit something.
No, you don't sound if you don't hit anything. Okay. So here I restart. But now in order to make it sort of more interesting, of course, we need to create some kind of loop here, right? So let's start to work on what we can call a little baseline. So we can start playing a split token here. Now you hear how it plays a second note when we hit something. Okay. I do a stop token there. I think I want these arrows here, so I can turn that down. Just to see what it sounds like now. Like so. And let's continue on our loop.
There's a score on the left hand.
Is going to call the score, yes. No, to remind me. Okay, so now we have a little problem. What's the problem? It's a lot of stuff going on, right? And the problem is that this thing here has sort of feeding lots of stuff into this loop. So that was placed in observation this absorb token there to sort of make things a bit more controlled. I'll try again. Now it's sort of a little bit groovy at least. Okay. So let's do something with the other start token up there. So we can just, why don't we just make a loop? Like so. Let's see what that sounds like. That's the fun thing here. You can just come up with an idea. It's quite pictorial. You can sort of draw figures here and sort of see what does that sound like. And I spent an awful long time yesterday just doing this, so I didn't get much sleep in the end. So, as I said, your mileage might vary, but I find this to be a lot of fun.
Therapeutic, I should say.
Yeah.
We're lobbying for the physical version.
Yeah, if you had a touch screen, that would be a much better interface, obviously. Or possibly some nice keyboard shortcuts or something as well. So the interface here is not particularly well suited for live coding, I have to admit. It's a bit too slow for that. I guess that's future work. Anyway, now we have a loop. So let's play and see what it sounds like. Yeah, kind of interesting maybe. We can observe one thing, and that is that this loop here is sort of 8 long. That loop up there is 10 long. So now it has a kind of polyrhythm, but maybe we didn't want that. Maybe we want some more simple. And you might also wonder, okay, it's all good and well to sort of play these counters here, but actually it's also quite limiting, because suppose you want to play 2 notes in quick succession that actually are quite far apart on this board. How do you do that? Well, it is what it is. We can't do very much about it, but we have one little trick to get a little bit further. And that trick is that for each, and this is something we added in the Arpeggigon, it's not in the Reactive. And the idea here is that we associate a repeat counter with each cell on the board. So when the player gets there, it stays there for a number of steps as we specify, and then it moves on. And if it happens to stay on one of these tokens, you can sort of play that token repeatedly before it moves on according to what the token says. And also, if you set that repeat count to 0, and that interpretation is that you just skip that position on the board. So for example, I can insert 2 holes up here and make this loop 8 long. So in a sense, using this repeat count, we can kind of locally stretch or compress this grid, if you see what I mean. So, we set the repeat count here too. And we have a color scheme for this. So if we increase the repeat count, it gets increasingly red. And if we decrease it, it goes black eventually. So now it's 0 and black. So the same there. Set that to 0 as well.
All the other ones are repeat count 1, is that right?
Yes, that's the default. So now we have sort of 2 loops that are 8 long, and it's sort of more of a traditional rhythm. Yeah. And then let me also show you the we have more than one layer here. Okay. So in this case, this layer is connected to the drum part of the synthesizer. So we can actually get some kind of a drum rhythm here as well. Now this is not a very good way of programming a drum machine, but because it's sort of quite random where things are, and it's difficult to get exactly what you want. But we can do something at least. We can get a little bit of a backing drum track here by doing something like this.
Which position will be a drum instrument?
Well, they all are.
Well,
Just-
that's MIDI notes.
Yes, yes, yes. So maybe we should have some more clever support or supporting drum tracks by allowing perhaps these to be configured to be specific instruments or something. We haven't done that yet. Anyway, now we should hear a little backing drum track here. Oh, it's a lot. It's a bit
Someone can rap with
sorry?
it. Someone would probably want to rap with it.
Yeah, possibly. I don't know. Anyway, so that's the Arpeggigon. I 5 minutes left or something?
Good question.
Yes?
Can you move this stuff around while the...
Very good question. Exactly, and that's part of the point, right? So, yeah, should I show this actually? Let's do that. Let's go back to layer 1. Sorry. And now try to modify this somehow. Suppose I drop in a split counter here. And then we should start here. Let's do busy already. But now you hear something else. So indeed, I can perhaps break this loop. So yes, I can do things in real
If
time.
you want to restart, would you restart it?
No, just the loop.
Yeah. So with a bit of practice, you could in principle perform this, and perhaps also with a better user interface than I have.
If you want to do live coding without being a programmer, I guess this is more easy. Typing line.
Each way. Yes, as long as you're happy to be constrained by this particular way of using. But then again, sometimes these kind of constraints can be quite inspiring, I suppose. There are lots of examples in the arts where object constraints are used to do artistic effects. For example, there are people who write books without using the letter E in the short Arpeggigon. These parts, for example. Anyway, I should wrap up. So let me say a few words about the implementation. So we have seen a number of aspects of the Arpeggigon. Thanks to the gentleman in the back, we now know this is really interactive. Yeah. We have seen that we can add layers. I didn't show you actually additional layer, but we can add as many layers as we want, up to 16 or something like that.
Do you communicate between layers?
No. Each layer is completely separate. We have seen that notes are generally discrete points in time. But of course, we need to play notes slightly shorter than on the beat for natural interpretation. So there is more that needs to happen than just on the beat. So we actually need continuous time as well for that reason, but also for other reasons such as if you want to sort of, well, the configuration you can change at any time, right? That's not tied to the beat of the music at all. And in the future, we might want to add things like swing to sort of play with the timing a little bit by lengthening and shortening pulse divisions. We might want to automatically do a crescendo or diminuendo, and that's something that takes place for a continuous time, and so on and so forth. So it's the case here for both needing discrete and continuous time, so hybrid systems. And of course, something like Yampa, FRP, is a very good fit for things like this, because Yampa supports both continuous and discrete time, because it's ultimately sampled, but the program is allowed to think up to a point as if we have both continuous and discrete time. What's Yampa is an implementation of in Haskell, and it supports signal functions, which is very much like what you saw in Faust before the break. Okay. Unlike Faust, because Yampa was not designed to be very, very fast or compile efficiently, but instead it's quite expressive, so we can do things like structure changes, we can add new things to the system as it runs through the switching combinations. And it has the support for discrete functions. And the program model is like this, so again, very much like Faust. And without going into a lot of great depths here, this is the architecture of the Arpeggigon. You can kind of see that this is a very natural fit for something like Yampa and programming with single functions. And in particular, here we have the graphical user interface. Out of that comes a signal, which is the current configuration of the board at all points in time. And fed into the various layers, that each layer can interpret what the board looks like and move around the layers. For example. Yes? 1 minute left, okay. So let me not say more about this. I can also just say that the other piece of the puzzle here is reactive relations. So Yampa is very good for expressing the core logic of a system like this. But we also need to tie in with the outside world, so we are using DTK Plus for the GUI, we're using Jack for the MIDI I/O. And these libraries can be very difficult to interface something like FRP because they're very imperative APIs. So we use something called reactive values and relations, to wrap this FRP core in a kind of shell that provides a bridge between this inner pure world and the outer, very effective and impure world. And what they are is that they are typed neutral values with SSIs and subscribe change notifications. So in effect, what we can do is that although we are working in the IO monad, we can set up a network of things that are connected to the outside world and also feed things inwards. And once this network is set up, we can just leave it as is and take care of itself. But having said that, because we are in the IO monad, when we have to, we can also do whatever dirty stuff we need to do to interface to these external libraries. So it's a quite nice sort of hybrid, halfway house between FRP and the outside world. And in particular, once we've done the work of interfacing with the libraries, there is no longer any need to worry about event callbacks and that's done with the interface layer, and they can just program as if they have some kind of signals on that outer layer and just wire things together. There's an example of that, and it might look a little horrible at first, but once you realize all that we're doing here is that we're creating various widgets, and then we wire them together, and then we just leave it to do its thing. It's actually morally quite declarative, I would argue, in how you can think about this piece of work. So I find that FRP works quite nicely together with reactive values and relations. Okay, so I need to stop. We did find that FRP and reactive values and relations work both in applications. Performance in terms of execution time and so on is okay, but the timing, as you probably heard, is a little off because we were quite naive when we generated the MIDI. We just output each MIDI event as soon as we can. What we need to do, of course, is to timestamp them and put them into DAX buckets properly. That said, if you run this on a better machine than I have, it runs pretty okay. Musical, well, again, I guess things differ. I think it's fun at least, and it's a nice way to explore particular things. And the code is available free online. Thank you.
That is sort of a way to symbolically compute the sequence that is generated by the automaton.
To save it,
Huh?
to save it?
No, not to save it, but to analyze it, to see, okay, this is what I'm actually doing. And
as long as you sort of have a static configuration,
yes.
I guess so. That said, it might not have a natural fixed point. So one thing we didn't, well, behind the scenes, we are limiting the number of players we get because if we have too many, everything has grinds to a halt, so we cap it. So I guess we take that kind of things into account as well. We actually want to randomize this and see what this nice really is. I haven't thought about that in great depth, but it's a very simple system, so I would think that it should be possible. Yeah?
Is it like the space that the tokens move around in? It's very deliberate, right? Is it possible to make a conjecture that if you don't have any calls, if you don't play with the delays, then anything you do is going to sound good? Or
okay, what do you mean by sound good? I guess it's up to the listener to decide what sounds good.
Well, like you could type check with Mezzo.
Yeah, and explore that. One thing one could do is, of course, you could have different intervals on this. Again, that would tie in with the talk we saw this morning, and that could be potentially interesting. Yeah. Yes?
Yeah, I was going to say about the link to the lattice from this morning. I think the arrangement of notes you had is more a combination of the fact that hexagons tile the plane and you have a palette of 12 notes or scale of 12 notes.
Right.
So do you think if you had a scale with a different number of notes, you could find a different tiling system maybe not regular polygons, but something that would make it work. I wonder if that would be a possible generalization.
Someone's done a similar I've seen videos of someone taking a keyboard laid out in that sort of format and then taking it apart and putting it back together so it can be used to play the Bohlen-Pierce scale, which is a 13-note scale. So I think it's in principle possible. And you can look it up on YouTube if you want.
Okay, perhaps we go to the